Okay, so we can start. So today we've got Raffael Stenzel talking about higher colimit topologies.
Thanks to the organizers for having me again. Yeah, so without further ado, let me start. Also, I have to say it's my first Blackboard talk in the last 2 years, so I hope I get the pacing right. I'm not very confident about that. All right, so let me start with a little motivation before I dive into the examples I actually want to talk about. So first of all, this is a talk about sheet theory. And just a sentence. Sheet theory is the theory of continuous functors. That's the wrong way around there. Over topological space. That's unreadable? Yeah. Awesome. Okay. So by topological space here, what we mean is the site. Right? What the site is tuple C tau for category C together with a notion or collection, say, of covers. And what continuous means, well, that is really context dependent. This will be part of the talk today, right? So to say a bit more about this is that functor classical context of type C to B where by default D is the category of sets or the category of groupoids, something along those lines. Is a sheet. Or tau. If where do I continue? Given a cover this tau sequence is an equalizer diagram. Here, this is the assume just for simplicity for the case that C has fullbacks, right? If C doesn't have fullbacks, you can write still a sheet sequence down. It looks a bit different, but in the case C has fullbacks, this is actually correct. So a cover is a choice for every object C in C, a collection of objects over it, and then we can abstractly axiomatize the notion of covers on the whole of the category C, which then behaves well with the notion of a sheet over it, right? So in some sense, we say that the value F is a sheet if the value at C can be reduced to coherent values on the components of a cover. So this leads to the notion of Brody topology, namely Brody determined by covers, and hence by set index collections over yeah, object C and C, right? So these are vectors of this form, I and I, where I is a set. Furthermore, so let me say some random collections of objects. Do such. Oh yeah. Sorry. So Grody topology, if you remember from classical topos theory, then Grody topology, let's call it J. Then a J sieve, right? So this is an element in J, which can be represented as a monomorphism sitting on the representable in the category of accretions over C. Which was generated. Consists of the maps colimit C, right? Which really exhibit the lift to one of the components. Right? And
Raphael,
yeah.
why are you emphasizing objects up here? I mean, Grothendieck topologies are determined by the covers, right?
Yes. So yeah.
Morphisms. So,
yeah, but we are objects in slides.
Okay.
The
Yeah, no, it's just you just wrote C sub I in the brackets sort of.
Yeah, sorry, no, that was just a typo.
Okay.
So the emphasis should be on this part.
Okay.
Instead.
Okay.
And two such generalized elements G, let's say they have the same domain, right? Of the set S coincide in S, right, in the pre-sheaf S, if and only if they coincide as maps from B to C. So there's no further data in the notion of identity. If they coincide as generalized elements. Is presentable, which is to say just as maps from B to C, right? Yeah. So on the other hand, let's look at the category theory. So you will not see immediately whether infinity comes in. Let's put this forward already. The infinity categorical context allows for the definition of proof relevant depending on what you say algebraic, may also be a adequate attribute in this context. Colors. Right? It should be put in contrast to the fact that here we have maps which merely exhibit the lift, which means that we just want the information, we want the property that there is a lift. We don't really care what the lift is, right? Or that the lift behaves a certain way with each other. So on the other hand, we can consider covers, which are diagrams into a slice where this is not necessarily a set. Which then generate let's say group sieve, which is not a sieve, by instead of considering, well, we still consider the same thing really, but it will not necessarily give us a mono, but we can consider this map, this diagram into the slides, and then post-compose with the innate embedding to three sheets of a representable, and take the formal colimit. So what we obtain is from a colimit of this composition into then there's another sentence, the general equivalent sieve whose generalized elements are again in here, but now not such that they exhibit some lift, but actually lift is part of the information together with the specified so the formal colimit, and because representables, right, this will have domain representable again because representatives are tiny, they commute with all colimits. So this is just to say it's a lift to a specified component of F. Now it gets more interesting if we consider the notion of identity between two such generalized elements, right? So two such generalized elements, say F together with a lift, and G together with another lift, coincide in the formal colimit if this guy coincide. And this is in general much more complicated, right? So in here, to say that two elements of the mono here over the one representable are equal, just really reduces to them being equal in the representable. To be equal in the formal colimit is much more complicated, right? Heuristically, I mean, we want to have a zigzag we want to have a zigzag within the diagram of F, which witnesses that equality. Yeah. Okay, so when I say this, why am I singling out infinity category theory here, right? I mean, this is just a general remark. So so in ordinary category theory, we study sheaf theory as well. A sheaf theory here is a category of continuous functors over topological space, and then there is the notion of a Grothendieck topos, right? Which, for the sake of distinction here, is abstractly axiomatized, right? As, for example, a left exact localization of a sheaf category, or accordingly as a locally presentable category which satisfies the Giraud axiom or any sort of abstract axiom. So in the ordinary setting, these things are the same, right? So we can consider the collection of Grothendieck toposes embedded in a given pre-sheaf category, and then we can consider Grothendieck topologies on our domain, right? And then there is a way to go in both directions, and this happens to be an equivalence, right? So if we start with the Grothendieck topology, which is just a collection of notions of covers over each object, what we can do is that consider these as sub-objects of the representables, and then just localize that collection, right? And then the class of theory gives us that this is the left exact localization of the pre-sheaf category here, and hence a Grothendieck topos. Vice versa, start with the Brody tuples, then we can define a Brody topology, which over C just consists of all the sieves such that S is an E equivalent. I'm mixing large capital letters and small letters, sorry.
Yeah, just a strange question, like maybe, I mean, it's kind of weird the way you mix slice categories and then the representable on C and stuff, because they're sort of the same thing, because the slice C over C is the group and deconstruction of the representable, right? So you could equally define a sieve to be discrete vibration over C, which is a sub-object of the slice, right?
Well, so it depends on what you mean by slice. So it's not, we have,
You know, like C over C, or the slice over an object C.
on the one hand, we have this federation, and on the other hand, we have this big, right? These are the maps and quasi-categories over representable, and these are.
Well, I'm just thinking of C over, I'm thinking of the slice category that you've written F in up above, right? Yeah.
This guy.
Yeah. That's the category of elements of YC, right?
Yeah.
So you could define a sieve as another discrete vibration S and a commutative triangle like that, right? So you could have, sorry to interrupt you, but you could have a map from S to the top of that.
Oh, yeah, okay.
Right? And I'm just thinking in those terms, it's just funny the way you mix the two. Like,
Okay.
you get it, because when you have a covers or diagrams like this, right? So you've got a map from I into C over C, and then essentially, I guess you're trying to generate the discrete vibration over C generated by the map, that map, which I guess is taken, it fits nicely in that world. It would be some final functor discrete vibration factorization or something. I'm just wondering, it seems you could put things in just the slice category world or in just the free sheet world, and it's just maybe a silly comment, but it's funny the way it mixes them.
Yes, maybe it's just yeah, most of this can be done without really so most of this can be done fiber over C, right? Without
Yeah, I guess that's
working. Yeah, sure. Yeah, that's true. It's not the part. I don't want to really put emphasis on that though, because I will work entirely with appreciative.
Okay, cool.
Okay, so there is this equivalence between, say, collections, right? Now in infinity category theory, we can still look at something similar, namely, we can consider the infinity topologies embedded in C hat. Now this is an infinity category, and this is the category of contravariant functors into spaces rather than sets. And on the other hand, there's still a notion of Brody topologies over infinity categories. Which is defined analogously. If you want, you could just define it as a certain collection of sub-objects of the representables which are close to set operations. And then you still can do the same things in both directions, but this is generally not an equivalence. So while if you start with the Brody topology, you can get a topos, and from the topos you can look at the monos and vertices. This will give you the same Brody topology, but the other direction doesn't work out. So in fact, this manifests to the fact that if you start with a pre-sheaf category, you take an arbitrary, a general topos embedded in C hat, so right adjoint is embedding, then you can look at all the monos inverted by this localization. and this does give you a topos, but these are generally not equal. You still have a map here. This is just an equivalent, right? Now there's some theory about on these partial localizations, which is covered in Louis' book, chapter 6, somewhere in there. So localizations which come from growth topologies are called topological. And then the second part here is of a specific form, which is called cotopological. Right? So this inverts only mono, this is generated by monos, and this will not generate any monos, which are not already equivalences. Right? Equivalently, this localization is cotopological if everything that is inverted is already infinity connected, right? Which is an intrinsically infinity categorical notion, which does not exist in a non-trivial way in finite category theory. So I will explain what infinity connectedness is later on. It's time to spend time. All right. So yeah. So a way to fix this is to instead of looking at these proof irrelevant topologies, which are monos, to rectify that in the way we have considered here, and consider topologies which are arbitrary maps over the representables, and axiomatize them correspondingly, and then we do obtain a map from the left to the right, from the right to the left, which does compose to an equivalence on both sides, right? So in order to make this work, we have to move in some way, in a heuristic way, proof of irrelevance to proof relevance. And this opens us the doors to define topologies which are invisible or maybe not even do exist in the world of finite. So I will not get that. This is all I will say to this somewhat general theory. I will just continue to now give you a way to give you a given topology, right? So I said that there is a notion of these proof relevant topologies. Now, how do I give you one? So if we look at ordinary category theory, then even growing topologies are rarely just given in full. Usually growing topologies are given by giving you a basis, right? So there's a notion of basis for growing topology. And in this case as well, there's a notion of basis, which is easier to define in the examples we want to. Right. So what is basis? So we will make use of a notion that was introduced by Anel and Ina Subramanian, instead of a modulator in an infinity topos. In this case, I would say on an infinity category, which is the domain of the appreciate infinity category we're interested in. We do the following. Romanian modulator on a small category is so I now work with the fibration setting a little bit because it's quicker to write down. Full self fibration M over C, which sits inside point pullback. That gives me a target vibration. Here we have the target vibration. Here we have the pre-sheaves. You can embed C with the innate embedding and say pullback. The let me know like this. Yeah, so the objects in here consist of the maps of representables in the appreciate category. And then we consider a full subvibration of this guy. So this is just a collection of maps of representables, which is codex data, basically, right? Such that each fiber you see, which sits in here, is a set, so it's small, right? It's not of class as it might be. And furthermore, it contains the identities. So in the paper of they show that each such modulator generates a factorization system by the according small object argument, and that these factorization systems are modalities in fact, meaning they're stable. The left class goes on the full base. Now we would want to localize them. Yeah?
Sorry, where does the pullbacks fit in here?
So the elements in here consist of just some mapping YC, right? And then we want that if this is an element, this is a
Okay, so you didn't write that down, or you did?
well, it's full sub.
Sorry, full subvibration, yeah.
So we would want to, because this is a small set, we can localize appreciate category C to this guy, and we actually obtain an accessible localization. But this is not yet necessarily that exact. So you want to add a condition so that if M satisfies the additional condition, when we localize it, we obtain a left exact localization, right? And one can see that a sufficient condition, which is easy to verify, is that if M is not only full-depth stable, but each fiber also is closed on a finite limits over each representable YC, right? So this is an additional composition. In some sense, full-depth stability means we can move via Cartesian action from one representable to the other. But if we stay over one representable, then we still can consider full-depth over there. And we want that each MC is closed under such finite limits over a fixed representable. And they continue to show that this is actually quite strong condition. There are weaker conditions, like that these guys are co-filtered. And then they define accordingly a notion of Lex modulator, which is a modulator, which is here co-filtered, and hence generates a localization, left exact localization. And they give another notion, which is called delta modulator. The problem with both of them is that they're still hard to come by. Right, we want a notion that is easy to, like, I have a candidate that I want to give me a basis of a topology, and I want to verify that it's in fact a modulator satisfying certain conditions, and both of these conditions are rather hard to verify, it turns out, at least for me in practice. So there's a third notion that sits in between those two guys, and we say that a modulator M1C is an identity modulator. The following holds that if we take a certain map over representable that's contained in them, right, and we consider, so this is an arrow of representable. And then we can consider sections to these guys, right? So we have two sections, S1 and S2. And what we want is we can build from this the equalizer over the diagram, over the representable of these two sections, which again sits over the representable. And what I want is that this is again contained in C. All right. So this is quite a closed definition because it's not two things in M, and what I want is again to be contained. Right, this is something I can verify. Right, so this is weaker than, so this is in general weaker than that these fibers are close to the finite limits. Under certain visual assumptions equivalent, but generally it's weaker. So we have the following lemma, namely that modulators with which are fiber-wise close to the finite limits, fiber-wise those sit inside the hit modulators. Those again sit inside and give you a definition of what Anel and Linus Germanium call delta modulators. Right? Now, why is this useful? It is useful because there's a corollary that localization as a delta modulator always gives you that exact localization. Right? So we do in effect depend on it. So the localization of the pre-shift category in the modulator is left exact. And is an modulator. Right.
You didn't tell us what a delta modulator is. did
Yeah,
you?
you can sure.
Or maybe it doesn't matter, like if you don't need to.
It doesn't
I was
really
just
matter.
checking whether you told us.
No, I did.
Yeah, okay.
I can write down. It's just
It's okay.
yeah. Yes. So in fact, this one can be more precise about this, namely that the modality or the factorization system generated by such a modulator is a left exact modality, so the left class close to finite limits, fiber-wise as well. And when we look at this localization, then we have an associated sheetification concept, right, which is the unit associated to the effective localization, right? Then this can be computed by an associated plus construction, right? So if you remember from ordinary category theory, there's plus construction, which after 2 steps converges. In this case, there is also a plus construction, but it only converges after transfinitely many iterations. But it's still something handy to make concrete computations. So just a quick remark, namely, every so-called, people calling them like that, every proof of the topology is generated by an hit modulator, in fact, by a modulator which is otherwise closed at the finite limits in a precise sense, in a precise. And every Grody topology is trivially right. So first of all, it's a modulator because it consists of monomorphisms over YC, and part of the definition of a Grody topology is that it's full-text stable, right? If you remember the definition from there. And why does the it part follow? Well, if we have if we start with an element in our Grody topology, this is a mono. So there is at most one section of the homotopy, right? So for every 2 sections, this is actually always an equivalence, right? Because S1 and S2 already coincide with the homotopy. So the equalizer is just all of YC. So this is of course contained in the Grody topology because Grody topologies contain all the isomorphisms, right? So in some sense, this is a total overkill, right? For the definition, we would just need that this is covering, but this is maximum covering. This is always an equivalence, right? Which is way more than we need. Okay. So let me finally start with the example. Discuss. Any questions so far?
So is the idea that you're going to give us some examples that lie outside the scope?
Some will, some won't.
Some will.
Yeah, so the examples, so they are not pathological examples. So I want to look at the 3 most popular, important, I don't know, examples from categorical logic, which are the extensive topology, the regular topology, and the coherent topology. Right, I want to look at these 3 cases and see how they behave in this setup. And you will see that they all three behave very differently. Okay, 10 minutes for each, basically, right?
You go a few minutes if it over time, it's not the end of the world.
I get that. That was included.
Yeah.
All right, let me see. Example 1, the extensive. This should go quick. Right? So what you can do is, if you start with a small fit category, you will find co-products. You can consider the following modulator. Which consists exactly of the maps induced by co-product inclusions. Y to Y. All right. So remember that the extensive growing topology is generated exactly by the families of co-product inclusions into co-product, right, of its components. And then that generates a sieve, which will give us, in fact, the -1 truncation, meaning the monomorphic part of this map. So what we do is, instead of forgetting, again, those lifts, right, what is a generalized element of such a map? Well, it is a map into the co-product together with a lift into the components, right? And we just don't forget the lift. That's all we're doing, right? So this is the spirit of the motivation at the beginning. So the proposition is that free sheet over C is an, let's call this an M cup, is that fair? M square cup, an M square cup sheet, meaning it's local, just a free sheet local for this, right? If and only X from C spaces preserves final product. And that's pretty obvious. But because this is just X of the co-product, and this is maps from here to here exactly the limits of the exactly product of the values, right? And you can see that M square cup is in fact a modulator whenever C is extensive. So we will not write that down, but it's the same definition basically as for another case. It means that pullbacks along co-product inclusions exist. They are universal and they're universal. And co-products are disjoint. Right? So co-products are disjoint, and the pullbacks along co-product inclusions exist, and they are universal. So the localization at this guy actually gives us an infinite topology. But this is also not surprising because if C is extensive, then X is such an M square cup sheet. In fact, if and only if it is the sheet with extensive Brody topology. Okay. So it turns out that we actually did not add anything new by looking at this in this proof relevant way. right? So a corollary, if you look at it in the ordinary categorical context, it's not hard to show that the sheaves for the extended program topology are exactly the ones which are preserved final product. And as a corollary, you get that you see small and extensive. And the associated localization is topological. Right? If you remember, it just meant that it's generated by growth topology, and this is exactly what this is. Right? So we do not obtain a new field. But it may be interesting to note that it's not only topological, it's furthermore very well behaved and tamed in different respects as well. For example, we have that. Oh. If C is small and extensive, then this infinity topos, right, which is just said that this category of extensive sheaves is hypercomplete. So what that means is I still didn't define what an infinity connected map is, but I said that every localization factors into a topological or by co-topological localization, right? And the second one always arises by localizing at a certain set of infinity connected maps. What hypercompleteness means is that in this topos there are no non-trivial infinity connected maps anymore. So for example, take the infinity carrier spaces, right? The terminal infinity topos. The infinity connected means that all the relative homotopy groups vanish. And then we have Whitehead's theorem, which tells us that such maps are already homotopy equivalent. Right? So for instance, that infinity topos is hypercomplete in that sense, because there are no non-trivial infinity connected maps. The proof is not hard, but I will skip it. A corollary is that if C is small and extensive on the left side, then this guy here has enough points. So remember that a point of an infinity topos is a map of the terminal infinity topos into it, which corresponds by Lefkan extension just to functors from C to S, which preserve co-products, which preserve finite limits and finite co-products. Right, so in some sense, these are the models of the extensive category in the category spaces. Right. And to have enough points means that there are enough points to detect equivalences in our infinity topos. Right? And the proof is just follows from the proposition plus coordinating completeness here. Basically the original completeness theorem, but we have to further assure that hypercompleteness is satisfied because it's here a case. All right, so the moral is that the extensive case is super well behaved, super tame, and there's nothing new that we add, which is not surprising because really what we look at co-products, the co-products don't add any new homotopy information. Right, all the topic information we have here really sits inside the representables. The forming and formal colimit, we would normally add new paths which would have to behave in a maybe unexpected way, but here we don't add any new paths. Right? Okay, so this was a boring case, but I just wanted to make sure to tell you that it is a body case. Okay? So example 2. Well, there's already a mistake to write this on the title. Go ahead anyway. Right? Let's say the regular case. Okay? So we can define what it means for an infinity category to be regular, which is this basically the same definition as for an ordinary category, just accordingly adapted, right? So imagine morally an infinity category is regular, it has finite limits and full-text stable image factorization, right? Is that enough of a definition? So then we can recall that in ordinary category theory, others on the regular category given by regular FEs in the way that we say that the current generated by the regular FE consists of all the maps such that there is a lift to that regular FE, right? Again, we forget what lift it is, we don't care, we just want that it is some. So the evident the evident modulator considered here, make this right algebraic or equivalent. It's given objects by just, well, take the unit embedding of such guys. Look at this, right? Because then the generalized elements of such a cover consist exactly of the lifts along such a regular FE. So although we follow just the same idea, this totally breaks down. So why does it break down? So the problem is that it is a modulator because of the regular F is a full-text table in a regular category, but it does not form an it modulator, and it fails to do so miserably. So the problem is that what we would need that if we start with a regular FE, right? Then what we consider, if you remember, what we consider by modulators are these equalizers, sections, right? Now, if we want to rewrite this a little bit, and because we work here just with a map and the image of the unit embedding, this would mean that if you consider pullback in C, if you look at the diagonal of that, then for this to be an immodulator, we would need that this is again contained in our modulator, which would just mean that the diagonal of an FE would have to be again a regular FE. And this is just not the case for general epimorphisms, right? This is in fact exactly the definition of a zero connected map in contrast to a -1 connected map, in case you are familiar with these sorts of things in model theory. So this fails in general, right? So it's not an modulator. In fact, it fails so hard that the left exact localization, and so we can look at the localization of this. This will not be left exact, but we can look at the left exact localization generated by it, right? And this is trivial. Like the sheets for this guy are exactly the constant sheets whenever C is well behaved enough. So in most examples, this gives us a trivial sheet theory. So what we can ask is still maybe what is the largest immodulator contained in our immodulator? And the answer is, well, what we have to do is just look at FP such that this is an FP, right? But if this is contained in our modulator, well, the diagonal of this FP must be an FP again, and so on for all higher diagonals, right? So this gives us exactly the definition of an infinity connected map. So a map in the regular category C is infinity connected if, oh no, right, if the nth diagonal of F is then regular FE for all n bigger or equal to 0. So all higher diagonals of F is still FE. So of course, in one category theory, the diagonal is always a monomorphism, right? So every epi such that it is, this is again an epi, if the category is balanced, this is an epi and a mono, this is an isomorphism, right? So if this is an isomorphism, if this is an epi, then this is already an equivalence itself, right? So the zero connected maps are already equivalences. I hope I get the end right here. And so on. If you do like two category theory, three category theory, the nth diagonal will be a mono. And then infinity connected maps are always equivalences. All right, just in infinity theory, they don't have to be. There are examples where this just fails in equivalence. Okay, and then you can show that then whatever proposition, if C is more regular, and this localization here, call it M, what did I call it? F infinity. So let's F infinity be the class of infinity connected maps in C, right? And then we apply the unit value to those. And this is left exact. So it gives us an infinity topos. But this topos here.
What's the definition of an infinity topos as a left exact equivalence?
Yeah,
okay.
That this infinity topos here is generally not topological and also not subcanonical. So to be subcanonical means that the representables are sheet-sorted. And this is not topological, meaning it's not generated by growth topology over C, and the representables are not sheet-sorted in general, which is in contrast to the regular topology, right? Because in the regular topology, the growth topology is subcanonical. And just the reason I want to just say that you can look at the topological part of this guy, right? Every left exact localization factors into topological followed by cotopological one. So we can look at the topological part here, -1. And then we can cotopologically continue. Also look at the other hand at the regular sheets for the regular purpose topology, and one can show that so this we would have no localization here. One can show that this factors in the topological part of this guy. Okay, now we know that this is subcanonical. So every representable is a sheet for this guy. which implies that every representable is a sheaf for this guy, right? Because to be a sheaf for this is harder than to be a sheaf here. But one can show that this is not subcanonical, and so we see that they too must differ. Okay, and the reason that this is not necessarily subcanonical is if C is not hypercomplete, meaning C has non-trivial infinity connected maps. That means that there are objects which know that these are not equivalences, right? Which means that these are not sheaves because they don't send this map for that specific infinity connected map to an equivalent. And we can in fact show that also there's in general not a map from here to here, and there's not a map from here to here either. So these two leaves kind of just non-trivially branch. They do not lie to each other. So it's a kind of a weird picture that we obtain here, right? They're not equal, they're not even comparable in general.
Can you say what the sheaves are for this?
Well, so these are the.
Yeah, okay, maybe.
It's a pre-sheaf from here to here, such that it's kind of explicit. Such that for all infinity connected maps, they send the equivalences, right? That's right. Okay. That's it. And the points, even the points. So what we do have is that what's kind of interesting is that we can look at the points of irregular sheaves, right? And it actually happens that every point for irregular sheaves is a point for this infinity purpose here. Okay, so in some sense of points we do obtain an inclusion while these are generally incompatible. The reason is that points are maps from C to S, which preserve which preserve finite limits and preserve effective epies. And then they, of course, if they preserve finite limits, they preserve diagonals, right? And if a map is infinity connected, then it sends an infinity connected map where every diagonal is an effective epi to again an infinity connected map. And infinity connected maps in spaces are equivalent. Yeah, the second one is irrelevant. But yeah, so every point here is a point here. Okay, great. I have 5 minutes left for the example I am most, which is the most interesting, I'm afraid. Awesome. Which is the coherent case. Let me see if I can set this. The topology. Maybe another name that might be adequate for all right. Where am I? Yeah. So let's if we look at ordinary category theory, then what is the coherent topology, right? At the coherent topology, we look at collections of objects over another object. Now, in the extensive case, we wanted that this is an isomorphism, right? Now, in this case, the coherent topology, we say that the collection of the CIs is a cover, but the co-product is antimorphic over the base, right? And again, we say that a map here sits in a covering set if an ornament that is one of these guys. Now, what does it mean for two of those? Lifts to coincide in the associated covering set. Well, it means that let's say S1, S2, those coincide with the associated covering set if they give us the same map in C. Now, what does it mean to give us the same map in C? It means that we can look at these pullbacks here, that we obtain a lift into one of these pullbacks, which give us the two maps down on the individual components, right? But more generally, we can consider diagrams of more general shape and look at, as we did in the very beginning, two relevant sieves which are of this form, right? Where we take it from a column. Indeed, these covering sieves are similarly of such a form given by the diagram, which is given here by the co-equalizer of these two maps over C. Then we want to know whether there is a map here. Of course, again, as I said at the beginning, this is just to give us a map in each one of the components. But it becomes interesting if you want to know two such lists are equal, and then two such lists are not equal if and only if they coincide here, meaning having a map into the fullback, but they're equal if and only if they coincide in the formal colimit, which is a more complicated notion generally, right? So there's a difference in the notion of equality. Now we want to obtain an hit modulator from these guys, right? We want to know, well, I want to look at the sheaves being the pre-sheaves which send certain colimits to limits, right? And therefore we need to form an hit and an identity modulator. So to obtain which consists of such maps here. Such that something is satisfied. We need that if we start with a map like this, we take the fullback. Colimit Fi times Fj over the colimit F. Colimit Yf, little y's. Here's the diagonal, and here is this fullback. And then these equalizers we looked at in the definition of identity modulators are basically corresponding to these fullbacks here, right? Which are because these are fullbacks of the algorithm, right? If you remember the definition of equalizers, being given by the pair of maps here and take the fullback on the algorithm. What we want is that this guy needs to be again an M, right? So what that means is that for every pair I and J and I, you need a diagram over some other category into this slice here. Such that the colimit of this functor is this object, right? And such that that this map here is the formal colimit of this functor. Okay, so what this means basically is that if you look at this diagram and see, right, we can look at components, we can look at the fullback. Now, instead of asking that this is part of our diagram, it's with it here, we don't need that. What we need is that this is as well, so this is covered by our diagram app. We want that this is covered by another diagram with certain components, such that there is not necessarily a lift from this end to our formal colimit, which basically would mean that there is a lift into a specific component together with a zigzag into these guys. We don't need a global lift into such an FK. We only need to be able to decompose into small parts such that every small part exhibits a lift into one of these components. Right? So in some sense, we want that these pull legs can be decomposed into small components, such that the equivalence of these colimit inclusions is witnessed not only in the colimit but already in one specific component. So we want that all higher homotopic data can be computed in the components. Right. Okay. So I'm running out of time. The point is, so okay, I'm going to make this short in 1 minute. So one will see that one cannot take all diagrams. Right? In order to form such a big modulator, it can be quite tricky, and we have to impose conditions on our domain category I and on our functor F, so that the collection of all such diagrams actually gives us an identity modulator. So this yields the definition of what I call covering functors. And it's quite a nice definition. Like, it makes homotopically quite a lot of sense. It wasn't on purpose. I just assumed what I needed to make this work, and the definition that came out of it is quite nice. And depending on how much structure your starting category C has, these are actually a lot of functors, right? In the beginning, it could be quite overwhelming, the definition to verify it. But if C, for example, has descent for diagrams of this form, then every functor with a domain that is full-backs, that preserves full-backs, is a covering functor. And so, long story short, what we obtain is a notion, like a modulator of kappa covering functors. Whose sheaves are, I didn't tell you what a kappa covering functor is, but whose sheaves are those functors, are those three sheaves which send colimits of kappa covering functors to limits of well, to limits period of spaces, right? And then what one can show is that we have this topos here, and that in fact the kappa coherent topology sits in between those guys. Let me call this these are the kappa coherent sheaves, these are the kappa covering sheaves. And one can show that this is in fact the topological part, and that this is the co-topological part. Right. So, and I think I have shown in the past few days that these are also generally not the same. So the difference between those guys is very subtle, and it can only be seen in infinity theory because this part here doesn't, it vanishes in the final case. So we get a more refined notion of sheaf, which has many nice properties, and it's quite fun to compute and play around with it. And I hope that this might be interesting for applications in high topos theory. For example, maybe towards a theory of infinity classifying infinity toposes from tangent type theories. I hope that this notion of covering function might actually be strong enough to look at things like inductive types and things like that, or certain inductive types at least, that then may be interpreted through points of this theory. Yeah, sorry for running over time, so that's it. Thanks for the attention.
Does anyone have any questions? Maybe I can ask questions. So are these the first examples of infinity topoi that are not obtained as topological localizations or something, or localization? No.
No. Okay. So in fact, in order to construct my examples in the regular case, I said that it's not always topological. Mm-hmm. I use those examples that are known and put them into machinery. Okay. Show that these are not topological. Okay. In order to show that. So again, I'm not 100% sure of this. I have to verify this, but I think I've shown an example. Again, there I use that. I use known examples. Okay.
So this last thing, it reminds me of the thing called hypercover. So it looks very much the same. So is it related?
It is related, but not in a not in a concept. So it is related in the sense that so the notion of infinity creating map is very much related to the notion of hypercover, right? So every sort of localization of this form can be generated by hypercovers, by collections of hypercovers. So this is related in the sense that we obtain in the end an infinity tuples being generated by something. But I wouldn't know how this relates specifically to this specific notion of cover coverage. I mean, in a way, what I want to do is move away from this dichotomy between topological and co-topological things, because it somehow comes. It seems that it comes from a sort of classical understanding of non-classical structures, right? Because we always want to decompose things in epipolynomials, right? And then we want to look at the epimorphic part and monomorphic part. Up to a certain degree, this works in physical theory, but up to a certain degree, it does not. Right? And I mean, the notion of a hypercover is again based on, well, instead of looking at one epi, we look at a family of epis. And I thought of moving away from being so fixated on topological stuff and things that are generated by models. So, for example, this whole idea about these generalized topologies, these group-level topologies, these modulators, right? I just look at general maps and just work with them, rather than first looking at the monos and then look at the topological part, and then there's some formal stuff left, and we're dead. I don't really see how that doesn't always necessary. Let's say put it like this. Like if you want to build, if you want to construct topology with some intuition in mind, then you can just do it directly using general arrows, rather than, well, using intuition, then first building a monomorphic part of the intuition, and then handling the rest, which might be messy. And indeed, sometimes it's different results, right? We have the coherent intuition, then we use that coherent intuition in the monomorphic part, and the coherent definition immediately, then we do not necessarily end up with the same thing.
Any more questions? Well, if not, then let's thank Raffael again. There might be a talk in 2 weeks, or if anyone wants to give a talk, just send me an email. So that's all for today.